Welcome everybody on Zoom. Welcome everybody in the lecture hall. Welcome everybody watching us from the future. My name is Ghislain Fourny. We spent the semester together looking at the beautiful world of relational databases, relational tables. This day today is a bit special because I'm not going to actually go so much into the material. My goal is more to give you a motivation for why we are doing this and the history of relational databases. Next week, we will start actually covering the relational model. A lot of the material of this course is actually material that is typically taught in the bachelors of computer science. So a lot of computer scientists take this material. This is kind of the equivalence course for everybody else. But of course, I will not assume all the prerequisites that computer scientists might have and make sure that you have all of the concepts and that I take them one by one. It's better if there's actually a projection in the lecture hall. All right, so let's get started. I love to do a comparison between physics and data science, because in fact, this is a data science course. Databases are database systems are part of data science. So I like to look at the way we do science as a matrix 2 by 2, where we have the most ancient disciplines that have been around for thousands of years now, mathematics and physics. This is the era where we didn't have any computers, right? So this was all with our brains and maybe writing a little bit to remember things better or to help the reasoning. And this is really based on our thinking with our brain, right? The main difference between mathematics and physics, one might argue, and I know that not all philosophers might agree with me, mathematics is kind of necessary in the sense of model logic, in the sense that you can just do it in your head. You don't need to go to the world and experiment things. You can just figure things out just by thinking, like 1 + 1 = 2 and so on. And you can actually derive a lot of things like this just by thinking. When you want to do physics, it's different. You have to, of course, you can build theories and so on, but then you have to go out there and experiment, right? You have to formulate falsifiable assumptions and then run your experiments, and then you see if that confirms or at least does not deny your theory. Of course, there are still a few physicists the theoretical physicists who can do a lot of things from their armchair, right? But at some point, you need to run experiments. But recently, as in probably in the past 100 years, maybe even less than that, we automated a lot of things. And so computer science was born. And at ETH, for example, it's been around for a bit more than 40 years now, the Department of Computer Science. Before that, it used to be with the Department of Mathematics and Electrical Engineering. And computer science actually is not just about computers, right? It's about all the notion of computation, complexity theory, algorithms, and so on. And there is a quote that I kind of like that basically says that if you think that computer science is about computers, it would be like saying that astronomy is about telescopes, right? So it's a bit the same analogy. And finally, data science, which is the fourth quadrant in here. And in a way, data science is a bit the physics of computer science. Because computer science, you can kind of also do in your head, right? This is all theoretical and so on. But data science, you have to collect data from the real world, and then you have to analyze it in order to discover things about the world. All right, so these are the 4 ways kind of doing science and discovering things. What I hope I will be able to show you today is that this whole thing, computing, databases, it didn't just start in the last century. In fact, it's thousands of years old. And even Plato back then, that you know lived a long time ago, he knew that you cannot just base yourself on numbers. You actually need to have knowledge extracted from them. And a lot of the motivation for information systems is basically this. So I will go ahead now with a history of databases and database systems in order to put everything in perspective. And I'll start with the prehistory. Of course, I will need to define what I mean with prehistory and history, right? Because it's not exactly the same thing as historians would define. It's really specific to databases. But basically, if we try to find the earlier times, the earliest times at which we actually stored data, I think it was in the antiquity and perhaps even before. It's the idea that people would remember events in their memory, and they would tell each other and tell their children, who would tell their children, who would tell their children, and then it propagates and propagates and propagates by word of mouth. Of course, it was done by speaking, but also by singing, right? So songs were actually also very important back then. Of course, the information that got transmitted was not absolutely everything, right? So there was, of course, a bit of know-how, but it was a lot about all the kings and the emperors, so all the people who had power, whose stories were communicated, right? So this was already, I would say, perhaps when we settled, it was 12,000 years ago, I think. If you want to really take it thoroughly and to the next level, you could even argue that databases are at least billions of years old if you consider our DNA to also be data, right? In a way, it's instead of base 2 as computers, it's in base 4, but you could also consider it of data. But the data we control as humans, that's basically, it started when we spoke and sang. And then there was a revolution. In fact, this is what historians would qualify as the beginning of history. Because if we just speak and sing, information can get lost, information can get distorted, information gets forgotten. And so one day, our ancestors actually figured out that you could just use a device, or what we call a pen today. Back then it was with clay tablets that you would then heat up in order to freeze the writing. But you could just use symbols in order to represent your knowledge. I don't know if, I'm wondering if the light, can you see okay, the screen? Maybe I can slightly change a bit the lights, like this, maybe speakers. Maybe it's better like this? Yeah, okay. So our ancestors figured out that you could just write things, and this is actually going to last for thousands of years because we can see them today, right? So we still have this. Of course, we need to decode it. We need to figure out how this translates, right? But it actually persisted all the way to today. But this way of doing things, of just writing as text on the clay tablets, is only one of the types of clay tablets that we found. Because there is another type of clay tablets that we also found. And when I look at this other type of clay tablet I'm going to show you, it almost feels like I'm in a science fiction movie. Because this here is a relational database, it's a relational table, and it is almost 4,000 years old. So this is how old relational tables are. They didn't wait for the 20th century to exist, thousands of years old. And that means that tables are actually very, very familiar to human beings. In fact, I think that there were even neuropsychologists who ran surveys, and they found out that tables are even easier to understand than pie charts or this kind of graphs, right? So you can see the tabular structure because it has rows and columns, right? And they will keep us busy during the entire semester. What there is in here, the information stored actually corresponds to what is known as Pythagoras triples, right? It's the possible integer sides of right triangles, like 3, 4, 5, and so on. Of course, these are more complicated than just 3, 4, 5, but this was stored there. And back then, the reason why they knew triangles and right triangles had to do with the fact that there were floodings, and when there is a flooding, it's hard to keep track of who owns what land. So if you triangulate everything, this is what geometry came from, then you can keep track once the flooding goes away of who had what land, right? And so right angles were very important. Just for the anecdote, there are a few mistakes in the tablet that we know today, and because we are able to actually decrypt this. This is, I think it's a base 20 representation. But anyway, the reason it makes me feel weird is that it almost feels like a tablet as we know them today, right? An iPad or that kind of things, running some spreadsheet software. All right, but this was a relational database in the proper sense of the term, because a database means data. All right, then the next invention was printing. What problem did it solve? When you have a clay tablet like this and you want to make copies, you just have to do a new clay tablet. And there were people working full-time, in particular monks, who were just copying and copying and copying over all the writings, but it took a lot of time. With the printing press, we were able to suddenly make thousands or even millions of copies of the same thing all over and all over and all over again in a very, very efficient way with all these little letters in there. In fact, in German, Buchstaben, it's even in the word, in the etymology of the word, that this is how it worked. There's a small anecdote also, is that, do you know where we say uppercase and lowercase in English for the capital letters? And it's actually because the uppercase letters were placed in the upper part of the case and the other ones in the lower part. So this is why it stayed as uppercase, lowercase. Okay. And now computers, of course, maybe it's provocative to put it that way, but this is a non-event in the sense that the only thing that happened here is just acceleration. You know, we build things that are faster and faster and faster, but the notion of relational database already existed before, right? So computers allowed us to with the invention, in particular, of the discovery of semiconductors, to have small computers that can be very fast. Back then, so this is a computer, of course, not as we have them today, but back then you have to imagine that a computer would fill an entire room and it would eat the electricity on the scale of the city. So you switch on the computer and there is an electricity shortage and the blackout in the city. So this is just to make you understand the power that this actually needed. And in terms of computation, this can actually do less than the smartphone that you're holding in your hands, right? So this has evolved massively. All right. But from a perspective of databases and database systems, we are still in the prehistory. And why am I saying that? Because all the way into the 60s, the way that people dealt with data is that they would have files and directories, as you all know them from your laptop. They would store the data as files and directories and then use programming languages, like back then, maybe COBOL, Fortran, and so on. It would be today maybe C, C++, Java, or even Python, in order to query this data. The problem is that it's very complex to do this. And anybody, even today, who uses Python in order to query data sees the complexity of this. So there is a problem because a lot of people are actually implementing the same things all over again and writing the same code all over again in order to make this work. Which is why in 1970, so 1970 is really the pivotal year for database systems, where somebody called Edgar Code, this is his picture that you see here, had a brilliant idea. And his idea was, look, tables are something that many people are very familiar with, even for thousands of years. So why don't we say that when people deal with data, they actually deal with tables, rows, columns, and so on, but they don't deal with this. They don't have to deal with files and directories and how it's stored in bits and so on and so on. All people deal with is tables, columns, rows, and so on. And that's it. And the rest, how this is actually done, is not the problem of the user. Of course, there are going to be people who will build the software that is able to support these tables and so on. These people will, in fact, store it in that way, but this now is hidden to the user. And the name for this is data independence. And data independence is probably something that you will hear me say hundreds of times this semester, because this is one of the most fundamental concepts and ideas in database systems, right? So in this course, we will spend a lot of time studying the model and the algebra at the logical level of tables like this without worrying too much about the implementation. I'll just say a few words at the end of the semester on this. And then, of course, history continued, even though that actually came later. We will not really cover this in our course. But in the 1980s, this is when object-oriented programming became popular. You might have heard of C++, Java, and so on. And then there are a lot of people who tried to connect these object-oriented programming languages to database systems, right? So that was this era. All right. So now let's zoom back to our lecture and look at the scope, databases are very vast, right? So in the 2000s, there were, 2000s, 2010s, also key value stores, column stores, triple stores, graph databases, document stores, XML and JSON. That we will not cover. This is not part of the lecture, right? But just so you know that this exists. So basically, if you look at it from an abstract perspective, we have data that is really the numbers, the raw data, from which we can extract information, from which we can extract knowledge, from which we can extract wisdom. And so if you look at it with plenty of buzzwords like machine learning, artificial intelligence, and so on, I had to have these buzzwords in my lecture, of course, but we don't cover them. We are not going to do any machine learning or artificial intelligence. We are just going to cover databases. However, what you might be interested to know is that for many machine learning systems, this is what you feed in them. If you want to do classification, linear regression, I'm not talking about deep learning and neural networks and so on, but many machine learning systems actually take this as input. So knowing what a relational table is also useful to understand machine learning. All right. So this is where we are. This is this lecture, fall 2023, Information Systems for Engineers. And there is a sequel to this lecture that is next spring for those interested. That's called Big Data for Engineers. Maybe some of you actually already took it. Who took Big Data for Engineers? None of you? Sometimes people take it in the opposite order, which is fine too. But so at the end, this is the more recent evolution that we see in Big Data for Engineers, in particular this we cover in Big Data for Engineers. All right. And Big Data this fall is for master students in computer science. And what I'm not showing here is the bachelor's lecture for computer scientists called Data Management Systems, I think, or something like this. All right. Now, I have a question for you. And in this semester, we are going to use the Edu app, if it works. Had a few bugs in the last few days, but let's see. So we're going to try this. You can either go to your browser to eduapp-app1.ethg.ch, or if you prefer, you can go to your App Store or Google Play Store, or whatever it's called, to look for EduApp 3 and install it. It's an ETH, it's made by ETH. So try to go there. Then I'll switch my screen. And I'm going to cross my fingers that it works, because they had network issues. Thank you, Bowen, for pasting the link. All right, so let me see if I have, yes, it's right there. So we'll do a test question. And so this is when things go wrong. So normally if I press here, oh, it's working today. So they fixed it, all right. So first, I'd like to know what your main background is. So we typically have a few PhD students. We might have data scientists in continuing education, mathematicians, physicists from their armchair or in their lab, biologists, including computational biologists. We also have people from the ETH department, math, mechanical engineering, architects, management, technology and economics, robotics, chemistry, environmental engineering, or others. So I just want to see a bit the distribution right there. So I give the first time I give you more time to figure out how it works, but I will use it a lot this semester, this app. So we have 65 so far. In total, we have, I think, 220 registrations in the course. But I know that some people actually watch the recordings, and I even discovered there was a study by people in the rectorate at ETH that some of you do binge watching. So they basically wait until the exam comes, and then they watch everything just like a Netflix series. And so it's a common practice too. All right. We don't seem to have PhD students. I'm still saying it in case anybody listens. In some departments for the PhD students, you can get credits without taking the exam. That's one of the perks of being a PhD student. But in order to get the credits, you still need to prove attendance. So if you are a PhD student listening to us right now, please tell us so that we can make sure to record your attendance. The deal, I think, is 10 out of 14 weeks of attendance for the lecture and exercises, and giving answers to the quizzes. All right, so please tell us. All right, so you see, it's a very diverse background, which is exactly why the lecture exists, because I know that you're not computer scientists, so I'm going to make sure that everybody understands. If you have questions, please do not hesitate to ask them. It's very likely that other people have the same questions. We even have a module forum. We have a chat channel that you can use. So do not hesitate to ask us if you need anything. Let me now go back to the slides. And here I'm doing something tricky, because if I prepared well, it will go well. So normally I'm supposed to exactly land back to where I was with the slides. And that's it, perfect. So now I would like to introduce you to the team, the TA team. We have some of them here. Maybe you can come to the front so that everybody sees you. So we have here Marco, Panos, Alexandre, Bowen, who are here. And we also have, not here in the room, Yu, Shaoje, Amir, Vasilis, Xiaocheng, and you can see their pictures right there, right? So you will have exercise sessions that you can attend. There is no exercise session this week, by the way, right? So you don't have to worry about today. The first exercise session is next week, right? So maybe let's give them a round of applause to encourage them, and they'll be with you this semester. Thank you very much. All right. So now this is the menu of the course, what we are going to cover. So there will be several parts. In the first part of the lecture, we'll just cover the basics. I'll tell you what the relational model is. That will be mathematics. Then we'll go a bit to practical aspects of creating and modifying tables in an actual system on your laptop. Then we'll go back to doing mathematics. I like to go back and forth between the two, and we'll study the relational algebra. Don't be scared. The algebra sounds scarier than it really is. You will see it's simpler than it seems. Then we'll come back to practice in order to use SQL to query tables. And then we'll switch to something a bit more advanced, which is database design theory. What does that mean? It's just a set of best practices on how you should design your databases. That's pretty much what it is. So it's a set of rules and things that you should do if you actually design databases. We look at indices. Indices is what you probably already saw at the end of a book, an alphabetical list of words, right? That's called an index. And in fact, we have this also in databases, right? I think we have a PhD student in the chat. So please talk with the TAs and we'll make sure that we record your attendance. Architecture and storage is the only time that I will speak about physical aspects of a relational database, because of data independence, we are not supposed to see that, but still out of curiosity, maybe you want to know how this is done. And then we'll see data cubes. Data cubes are another shape. It's something else than tables, but it's very popular for business analytics, sales reports, and so on. So the sort of fancy reports that you give to the C-level executives, and how to query cubes. And then we'll have an outlook towards big data to motivate you to come back in spring, if I don't scare you too much. All right. So I think you get 4 credits out of the exam if you pass it. So there is the weekly lecture that is right now, so every Friday from 10 to 12. Then you have the exercises where you have a choice. You can either come Fridays from 4 to 5 or Mondays from 3 to 4, but not this week and not this Monday, so really after that. So the Monday session corresponds to the previous Friday session, right? So this is how they are coupled. All right. And finally, you will have the written exam. Don't be scared by the 3 hours, because it's only so you don't have stress. So one of the important principles at ETH is we don't want you to solve exams under time pressure. We really want you to think, about the answers and so on. So the exam, I keep saying my TAs, no more than 60 questions. When I say 60, it's 60 in the sense, multiple choice and so on, right? Not 60 big questions, 60 small questions. And so normally 3 hours is more than enough. Last time, I think we did it in 2.5 hours. I gave you 30 more minutes, but it's not going to be longer. It's just that you can take more time if you need it. All right. And typically, a lot of people leave before the end when we do this. All right. Okay. So that's the deal. Is there a question maybe on the link to online exercises? Maybe Bowen?
So there's a question. Will the link for the online exercise group be shared, or do I need to sign up for this particular exercise group?
So the way it works is in my studies, you can register for an exercise, and then on some of them, it's written that it's a hybrid exercise. So some of the TAs kindly agreed to do it hybrid. And then the Zoom link, I think we'll post it also in my studies. You'll see it there. And I think we'll also put it in the Moodle, right? So we'll make sure that you have the links. But please try to register for an exercise session. If it's all full, let us know. We'll find a way. But please try to register. If you want to attend online, then pick a hybrid session. If you want in presence, try to pick a present session. But even the hybrid session will have a presence room. So we will post the links. Did it answer your question? That's what you wanted to know, right? I assume so. Awesome. And again, nothing this week, right? It starts next Friday, the exercises. All right. Something else that we have, so we have a bit of infrastructure. So there is a chat server that is actually set up by ETH. It's chats.ethd.ch. And on the left, it's for staff. On the right, it's for students. So you should go to the right and start the student chat. Make sure you're connected there. Normally, I already invited all of you that were registered till a few days ago or 1 week ago. So if you cannot see the room, please let us know. We'll probably do a second round of inviting people. But it's a good place to chat with us or also with each other on the material of the course. The TAs will communicate to you if they prefer, if they guarantee answers in the Moodle. It's called Moodle Overflow forum, or on the chat. It's basically the TA's choice, right? You can still use both, but we give you a guarantee on one of the channels. Okay. This here is the URL to the Moodle, which is where all the material is. You will find the slides, the exercises, the what we call the exam magic box that just has a database system that will just work with Docker. Do you know what Docker is? Who knows what Docker is? Okay, some of you. So Docker is a way to easily run software without having to worry if you have Windows, Mac OS, Linux, or anything. It's standardized, and normally it will just work. Of course, as always, when you're a computer scientist, you know that when everything just works, it actually doesn't just work. So those who have M1 chips and M2 chips might have issues. If you have any issue, let us know, and we'll try to help. All right, and if you're registered for the course, then you should have access to the Moodle. You should use your ETH account. So if you're a University of Zurich student, please use your ETH credentials. Okay. So now that this is said, let's continue a bit on the overview of what we are going to do. Still have 15 minutes until the break. So we are going to deal with information. The name of the course is Information Systems for Engineers. So what is information? So when we speak or write, this is information, spoken, written language. There's also a lot of information that we draw. So not just tables and text as we saw on clay tablets, but also pictures, diagrams, and so on. And it's basically some representation of things that are in the real world. Now, as opposed to information, if I talk about data, what is data? It's something that is raw. It's raw material. And with data, you typically do two things. You can store it in order to query it, analyze it, and so on. So you can store it, and you can exchange it, right? So exchanging means you can store it on some USB stick, or you can store it online on the internet, over the web, and so on. So these are all the ways to exchange it. And of course, we don't do it in the same way. We'll see if you store the data, you use the interface of the database system. We'll see PostgreSQL. I'll show you how to do that. And if you exchange, then you might need to actually save it as files. Who heard about CSV files? Comma-separated values. Many of you, right? You can open them in spreadsheet software like Excel or LibreOffice or and so on. And this is a very popular format for relational tables. But I think that administrators, when they export data from a system, they don't like to use CSV. They prefer to export it as a SQL script. We'll also see what that is. Okay, so data, raw data, can be stored and can be exchanged. Now I like to make the comparison with wheat, flour, and bread, because this is pretty much what happens. So the data is a bit like wheat, it's the raw material that can be transformed into information. This is when you add meaning to it. What's the difference? So if I tell you, for example, I don't know, 821, doesn't mean much, right? Because I'm not telling you any context about that. But if in addition to a number, I also tell you what it represents, for example, if I tell you 220, and I also tell you it's the number of students registered in this lecture, then it's information. It's not just data, right? And then when you have a meaningful application and take it to the next level with business logic and so on, you have a meaningful application, then that becomes knowledge, right? It's very high level today, but I told you we are not yet getting into formalism just the first week. And so what an information system is, in the very wide sense of the term, it's a system, a computer system. When I'm saying computer system, it doesn't have to be computer, it's any system that allows you to deal with information. The reason I said it doesn't have to be a computer is that if you come back, for example, to the Library of Alexandria, like thousands of years ago, that was already an information system. A library is an information system, but you don't have computers, you have librarians, right? Who basically store the books and keep track of who borrowed what book and so on. So it's a program or set of programs that manages information. And today we do them with computers. Now let's dive a little bit more into the structure of the data, or how structured data can be. I'll first start with something very important, but it's very simple, in fact, but many people are not aware of it, even though that's the secret in order to have a system that is fast. It's the secret, and it's an extremely simple secret. Data has shapes. So we have tables like this, but this is actually only one of 5. There are 4 other shapes. Data can also look like trees. We call it denormalized data. We'll see why we call it that way in the lecture, but we'll not cover trees in this lecture. We also have data that looks like graphs. This is also not covered in that lecture. We have data that looks like cubes that we cover. I told you at the end of the semester, we'll cover cubes. And we have data that looks like text. It's just what you find in books. So there is no structure here. In fact, data that looks like text, you can also treat it as a database problem. And there is a whole lecture for bachelor students in computer science called information retrieval. And in fact, what is an information system that deals with text? It's basically a search engine, like Google, Bing, DuckDuckGo, and so on. This is basically dealing with text, the text that you find on web pages, right? Okay. So there is this spectrum with the shape of data that goes all the way from completely unstructured to structured. So completely unstructured is just text, right? Like this. And then it has more structure if you put it as a graph. So think, for example, of the VBZ map of the city. That's a graph. Then it becomes semi-structured. And then structured as a table, and a cube is even more structured, right? So this is kind of the spectrum of how structured data can be. And in this lecture, we'll focus on this. So unstructured can be text. In fact, you could also argue that can be an image too. You can consider it, it depends on the perspective, right? You can consider it unstructured, but you could also consider it has pixels. These have become very popular with generative AI, right? Now we can just very easily figure out what's on an image with artificial intelligence. We can generate them. It's incredible. That's not generated, that's a real one. Then there is audio, there is music. Back then, I mean, when I was a kid, we didn't have MP3 or we didn't have streaming or anything. We just had our Walkmans, or, you know, this is how we listen to music. Now it's completely dematerialized, right, as bits. So audio is also some kind of data. Then we have video. Again, back then we had to go to some place in order to get the CDs or DVDs or even tapes back then, because CDs did not even exist. Now it's all dematerialized and streaming over the internet. This is one, I think it's a century-old movie, this one. I think that what happens, he's looking in there and the other one is going to press here and then he's going to get water into his face. But that's a very famous old movie. L'arroseur arrosé, I think is the name in French. So this unstructured data is very raw. It doesn't have any notion of columns and columns and rows. It doesn't have anything explicit. It's all implicit, right? We as humans, we grew up among that, and we know how to read text. We learn to read in primary school, and we kind of automatically see. We don't even have to be trained for that, right? We just kind of do it automatically. But that's the fun part, because for us it's natural. But then go figure how to make a computer do that. That actually took us a lot of time. Now we are getting there, but yeah. So in this data, you have characters. You might have the grammar of the language, the pixels. Yes?
You keep talking about unstructured data. All the examples of this sequence is unstructured. Is a different way of describing a sequence of data, or is that more different kinds of unstructured data?
So I guess a sequence is one way of putting it. If you maybe have ChatGPT in mind, that it's just a chain of words, or the blockchain. I'm saying a lot of buzzwords these days, right? But so here you have a sequence. This is one way. What I mean here with the fact that there is no structure, the only way to see a structure, I mean, somebody in the 21st century would see a structure with pixels, right? Because you could see, okay, these are just pixels and there are rows and columns of pixels. But back then, if you didn't have yet the digital world, this is just something you see, right? These are the photons reaching your eye, but there is no specific structure that would be explicit, right? Everything is implicit, and we have basically our eyes and brains are actually able to deal with this, right? But it doesn't have to be a sequence. It can be, I would argue that even a sequence is already kind of a start of a structure, right? It's very hand-wavy what I'm telling you, but again, this is because we don't get into the formalism yet. What I really want you to see, I mean, this is the most important one, right? That you basically have this spectrum. We're going to focus on the structured parts. There's rows, there's columns, it's highly organized, there are constraints. Constraints are an important part also of the structure. And on the other hand, you have the unstructured data. Maybe I can add another dimension of unstructured data, is that unstructured data is much more difficult to deal with, much more difficult than structured data. Because structured data, this is why they were figured out in the 70s for the automation, the relational database systems. But all the rest, we only harness them later. Like even search engines over the internet, I think there were early ones before Google. There was Alta Vista and so on. So in the 90s, there were a couple of them. That's already 20 years later. All of these, the graphs, the trees, that's, I would say, is perhaps 20 years old now, a bit more than 20 years old. So this is more recent. So the structured data, there is this notion that it's much easier to handle because of the structure that there is in there, right? And unstructured data, if you go back to, again, libraries, because libraries are a great example of an information system. Again, when I was a kid, we didn't have this full text search. Like now you can just type in a search engine words and you will find where it is. Back then, when you went to a library, you could only type keywords. So the librarians, they would basically index the books by typing a few words that correspond to the book. And then you had a computer and you could make a search, but you were unable to actually search the content of the book. The only thing you were searching was based on what the librarian prepared, right? So this is how tough it is to deal with unstructured data. Maybe one of the ways to think of it is as opposed to structured data. So at the end of the semester, you'll have a pretty good idea of what structured is. Then you can understand unstructured as a contrast to structured data. Did I somehow answer your question? Yeah, all right, thank you. I told you, right, today is a lot of hand waving. Next week, we're getting into the actual material with precise stuff. Okay, it's just a motivation today, really, an introduction. Audio, video, yes. Now, so this was structured. What if we add a bit of structure? So this is the sort of things we cover in big data for engineers. You could have data that starts being organized as some hierarchy or some arborescence. You can think of a genealogical tree as an arborescence, a tree. So maybe XML, JSON, YAML might ring a bell to some of you. So this is that kind of structure. But when you have that, the reason it's called semi-structured or not fully structured is that it can be very, very, very messy, right? And we'll see that next week, in particular in more details. But when you have a table, if I come back here, when you have a table like this, even if you have 1 million rows, you have the certainty that every row has exactly the same attributes. So if, for example, you store people, let me take the example of, I don't know, Seraph that organizes the paying the fees for television. They have a database with probably, I don't know if it's 8 million people, maybe a bit less, it's the Haushalte, but let's say 8 million. So you have 8 million rows. Then you have in every column, everybody has a first name, a last name, maybe a social security number, the month in which they are billed, and so on and so on and so on. This is what highly structured is. But in semi-structured data like this, you might have a lot of records in the same way, maybe a lot of people, but you won't have the same attributes every time, right? So it's a bit of a mess, really. And there is something you can do, again, that's covered in big data, that's called validation. You can actually add some constraints, and then instead of drawing trees like this on the left, which can be a bit complex, then you draw something that starts looking at a table like a table, even though it's not quite a table yet, right? So this is what we call a data frames. Who heard of data frames? Because that was a buzzword as well at some point. Yes, pandas and so on. So a data frame is kind of semi-structured. It's not quite a table yet, right? All right. And in fact, the reason we have that is simple, is that even though we invented in the 70s this structured data in relational table, the real world is not perfect. So not everything in the real world fits in tables, right? That's diversity. That's the beauty of it, right? But when you have in the real world something that doesn't fit in relational tables, then you need to invent systems that can deal with this, right? And so in particular, when you clean up and prepare data for machine learning, then you have to deal with this. And then you try to turn it into a table, then you use the table, right? So that's an example taken from, I think it's 6 Swiss Exchange in Switzerland. We are in Switzerland, right? So I have to do a few, mention a bit of banking or so on. But anyway, this is a list, a structured list where you see it's a list of companies, a list of stocks, and then you have in every column the same information, right? How can we see? I'm checking the time because there's going to be a break. The idea is that there is a structure here, right? There is the name of the company, there is change, last, bid, ask, and so on. And so if you add more records or more rows in that table, the structure remains the same. It's known in advance, right? So this is what structured actually means. Another analogy that we can use, and in fact, I encourage you to do it because this is there are a lot of commonalities, it's spreadsheet software. So it doesn't matter if you use Excel, LibreOffice, FreeOffice, and so on, it's all the same. But basically, you have the same idea of having rows and columns. Spreadsheets, still be careful with them because it gives you this feeling of structure, but it's easy to get things wrong in there. And there are examples in the past. A few years ago, I remember that a government issued data and somebody offset a column in Excel, and the data was wrong, and that ended up in the press. And of course, it didn't give a good impression. So this is one reason why spreadsheets are nice, but if you use a database system, it's even better because you cannot do these kind of mistakes. But a lot of things I'm going to explain to you in the lecture can be understood with spreadsheet software. So for you to understand the concepts, it's actually very useful, and I'll probably refer to spreadsheets. All right, it's 11. So I expect that it's going to ring in probably just a few seconds. So we'll take a break, 15 minutes, and we'll be back at 11:15 to continue. So I'll see you then. Thank you very much.